In this lecture, we are going to find the portfolio with the maximum Sharpe ratio in code. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So let's start by figuring out, what is the risk-free rate? Basically, you can just Google this and you will find a link to stlouisfed.org. From there, you can look up the relevant date and find the 3-month T-bill rate for that date. Okay, so I chose 0.03 because that was the approximate value for the dates we are looking at. Note that this is not 3%, but in fact 0.03%. In other words, this is a very tiny value, and this justifies why many people approximate this value as 0. However, I think it's useful to go through the full calculation. Note that, since our data is daily, we also want to divide by 252 to get the effective daily interest rate. Remember that, although the T-bill rate is for 3 months, the rate listed is an annual rate. Okay, so next, we're going to write a function that returns the negative Sharpe ratio. Why the negative Sharpe ratio? This is because SciPy has a minimize function and not a maximize function. So if we want to maximize the Sharpe ratio, we have to minimize the negative Sharpe ratio. Okay, so inside this function, we first calculate the mean and standard deviation using the usual formulas. Next, we take the mean, subtract the risk-free rate, divide by SD, and negate the result. Next, we're going to call the minimize function to find the maximum Sharpe ratio. So for the fun argument, we're going to pass in the function we just defined, neg Sharpe ratio. Other than that, you should be familiar with all these other arguments by now. So let's run this. Okay, so the optimization terminated successfully. By the way, notice how easy that was. If we were going to use quadratic programming, we would have to go through the work to derive the quadratic program and figure out all the matrices that go into the QP solver. Instead, we can just pass in our function directly and not have to worry about the problem having any specific structure. Next, we're going to assign the maximum Sharpe ratio and the corresponding weights to variables called best SR and best W. Now, you recall that earlier we did an experiment where we generated a bunch of random portfolios. In fact, this is another method of estimating the solutions to the various problems that we've solved so far. You can imagine that, after generating enough portfolios, you will have generated nearly all portfolios. And so, if you want to find the maximum or minimum something, you can just directly search through all those random portfolios to see which one is optimal. Of course, this is only approximate, since you would need to generate an infinite number of portfolios to get the true answer. However, it's worth trying to see how close we can get. By the way, this is known as the Monte Carlo approach, which is why I've pre-appended the variables here with MC. Okay, so to start, I'm going to initialize the best weights to none and the best Sharpe ratio to -infinity. Next, I'm going to enter a loop to iterate through all the risks and returns that we generated earlier. Next, I'm going to calculate the current Sharpe ratio, SR, which is the return minus the risk-free rate divided by the risk. Next, I check whether this new Sharpe ratio is better than the best Sharpe ratio we have found so far. If it is, we save this Sharpe ratio, and we save the corresponding weights. When we're done, we print the best weights, and we print the best Sharpe ratio. In the next block, we are going to plot everything we just found. So to start, we're going to first draw a scatter plot of all the random portfolios. we'll use an alpha of 0.1 so that these portfolios will be transparent. Next, we'll plot the efficient frontier as we did before. We will color this black. Next, we're going to plot the portfolio with the maximum Sharpe ratio found by our optimizer. Note that we don't yet have the corresponding risk and return. However, we can calculate these using the weights that we saved. We'll call these opt-risk and opt-ret. So next, we draw a scatter plot with just this one point, and we'll color it red. Next, we do the same thing, except for the portfolio found by our Monte Carlo simulation. We'll color this pink to differentiate it with the previous point. Okay, so let's run this. And what do we see? We see that the portfolio with the maximum Sharpe ratio falls along the efficient frontier. So that's a good sanity check. If this point were not on the efficient frontier, that would mean we got the wrong answer. Next, we can see that the pink point, the portfolio found by Monte Carlo, is pretty close to the portfolio found by direct optimization. In other words, if for some reason you couldn't use optimization, Monte Carlo will give you a reasonable answer.